So far in this module, we have explored how to look at black holes. Now we get to the fun stuff. Now we get to actually see what astronomers see. Let's examine the information received from black holes with various telescopes and find out how astronomers use this information to learn more. Active black hole binaries, like our friend Cygnus X1, are impressively bright in X-rays. Black hole binaries can be about 10 to the power of 10 times brighter than our Sun in X-rays. That's 10 billion times brighter. This means that in the X-ray part of the spectrum, black hole binaries really stand out. Stellar mass black holes have two main features in the X-ray band. The first we associate with the hot accretion disk. The material in the disks around stellar mass black holes is travelling so quickly that it can reach temperatures of millions of degrees Kelvin, which means that the peak of the disk's emission is in the X-rays. Earlier in this module, we mentioned that the emission from the disk would be blackbody-like. But what does a disk look like in X-rays, and what can this tell us about the black hole? The horizontal axis of this plot is photon frequency, which you may recall is inversely related to the wavelength of light. So as we move along the x-axis from left to right, the photon frequency will increase. This increase in frequency means that the wavelength of light is getting shorter. The vertical or y-axis is labelled relative brightness. The units of this axis are a little strange, and so we've left them off. We don't really need to worry about them at this point, though. All we need to remember is that things get brighter the further up the scale you go. If we now look at the spectrum itself, we can see the feature or the shape astronomers have associated with the disk. It looks kind of like a hill. We have a steady slope building from lower photon frequencies or longer wavelengths up to the peak at higher photon frequencies or shorter wavelengths. This steady slope is known as the tail of the disk. After the peak, there is a sharp drop-off or turnover towards higher photon energies. Astronomers call this feature a component of the spectrum, in the same way the disk is only part or a component of the black hole binary system. What would cause this shape? Well, the emission from the disk is thought to be powered by blackbody radiation. However, if we now plot our disk spectrum next to a blackbody spectrum, we can see that they don't quite match up. How can this be? The easiest way to think about this is to imagine that the disk is made up of a series of narrow rings. Each of these rings is emitting radiation at a different temperature. As we move inward through the disk from ring to ring, each subsequent ring gets smaller and hotter. The hotter the ring, the more the peak of the spectrum becomes shifted towards higher photon frequencies. Now do you see why the spectrum is not one blackbody spectrum? If we plot a spectrum of each of these rings and stack them all together, we get an overall shape that matches the observed spectrum of the disk. Astronomers call this the multicolored disk model, since each ring peaks at a different wavelength or color from the next. The multicolored disk model produces a close fit to observational data from accretion disks. While this model is simple, it's widely accepted by the astronomical community. It has been accepted because this model provides a reasonable description of the accretion disk emission and can provide key information relating to the black hole. The peak temperature of the multicolored disk model tells you the peak temperature of the inner ring of the disk. If this last ring is at the innermost stable circular orbit around the black hole, then this temperature can give us information relating to the mass of the black hole. However, we should note that although astronomers have used the multicolored disk model for decades, and probably will continue to do so for a while to come, this simple model has some issues. Why do we have these issues? Well, it is at this point I should remind you that astronomy is different from many other areas of science. Most scientists come up with theories and then try to test them by looking at the objects they're investigating, by picking them up, by turning them round, by exploring things from all angles. Quite often, scientists can poke and prod things they're interested in, maybe even pull them apart, and hopefully put them back together again. This is not the case in astronomy. All the objects astronomers investigate are out there in space. They are too far away for us to visit, yet. And so we only have the small amount of light that they send in our direction to help us piece together their inner workings. So what are the problems with the multicolored disk model? The first issue is that in order for the temperature of the innermost ring to provide information on the mass of the black hole, we have to work on the assumption that the black hole's accretion disk extends all the way down to the ISCO. But is this a safe assumption? Even the nearest active black holes are so far away that we cannot directly image the inner disk. As such, we don't know how safe it is to assume the accretion disk extends all the way to the ISCO, but we suspect that it does when the disk spectrum dominates. What other problems could there be with the multicolored disk model? Secondly, this model does not take into account the spin of the black hole. As we saw in Module 6, if the black hole is spinning, the ISCO can shrink from 3 times the Schwarzschild radius down to half the Schwarzschild radius. So, for a given temperature or radius, the spin of the black hole can change our estimate of the black hole's mass by up to a factor of 6. In order to overcome this issue, astronomers would need to also know the spin of the black hole. If the spin of the black hole is known, then astronomers will fold this into their mass calculations to improve our estimate of the black hole's mass. In most cases, however, we don't know how fast these objects are spinning. When we don't know the spin, astronomers tend to assume zero spin, knowing that this will add an additional error onto the estimate of the black hole's mass. The final issue with the multicolored disk model is that it's a very simple model. This model does not take into account all of the physics of the accretion disk. The material in the disk is incredibly hot and is thought to be some kind of plasma. Plasmas have been found to act like fluids. It is also thought that there are magnetic fields threaded through the accretion disk. However, to account for these factors, you must perform very complex magnetohydrodynamical calculations. These calculations usually require a few spare days, weeks, or even months, even with the help of a supercomputer. Observers tend to leave these calculations to the theorists and continue to use their simple toy multicolored disk blackbody model when playing with their data. As we mentioned earlier, black hole binaries like our good friend Cygnus X1 are bright in the X-ray portion of the electromagnetic spectrum. This is why astronomers often call these systems X-ray binaries. Their accretion disk spectra peak in the X-ray band of the electromagnetic spectrum, with a tail extending through ultraviolet waveband and even into visible wavelengths. How would this change if we were to move up the mass scale of black holes? If we were to consider intermediate or even supermassive black holes? More massive black holes are larger. Both the event horizon and the ISCO are found at greater distances from the black hole's singularity. This would mean that the innermost ring of the disk would be at a greater distance from the center of the black hole, and so will be cooler. As cooler disks emit at lower photon frequencies, the peak of the disk spectrum of a supermassive black hole would be in the ultraviolet part of the spectrum. Given that the disk of a supermassive black hole peaks in the ultraviolet, you might be surprised to learn that there are few observations of supermassive black holes made with ultraviolet telescopes. Most supermassive black holes are in galaxies that are moving away from us as the universe expands. Therefore, the ultraviolet photons that are emitted from the disks are significantly redshifted and can be observed in optical or even near-infrared parts of the spectrum.